Hello. In this video, we're going to look at what's called polar form. Now, believe it or not, there's actually more than one way to label points in the plane. For example, let's consider the point 4, 4. Well, obviously, it's labeled 4, 4 because we go over 1, 2, 3, 4 on the x-axis and 1, 2, 3, 4 on the y-axis. But what if there was another way to label it? What if there was another type of grid to put down? In fact, there is. If we put down a grid like this, a bit of a spiral grid, well, the point 4, 4 now looks a little bit different. Let's see if we could find out how this point would be written down. Well, let's look here. It appears that there are these concentric circles coming out from the origin. Each one of these circles has a radius of 2, or a radius of 4, a radius of 4.5, 5, 5.5, 6, and so on. Now, you might argue, well, okay, wait, this point 4, 4, shouldn't that be on the circle of radius 4? Well, not entirely. If the point is at 4, 4, what we really have is a little triangle here of 4 this way and 4 this way. To find the radius of that point, we would need to use a little bit of Pythagoras. So it's 4 this way and 4 this way, which means we're missing what the radius of this circle would be. So r is equal to the square root of 4 squared plus 4 squared. So 16 plus 16. So the square root of 32. Now, if you check on your calculator, the square root of 32 is approximately 5.6, 5.7 in there, which actually makes sense because if you look here, this is 4, this is 5, this is 5.5, and so we can see it's just a little bit past 5.5 in terms of the radius. Okay, so it's almost on 5.5 as a radius, but what else would we say about this point? We see that there are these lines that radiate out from the center. And it appears that those lines are actually angles. Pi by 6, pi by 3, pi by 2. Well, let's see if we could find out which one this is on. This one actually lies directly on one of those nice lines radiating out from the center. And it appears, based on our unit circle, that this is going to be 45 degrees, or pi by 4. And so if you were to imagine this as a theta, it looks like our theta in here, we could say, is equal to 45 degrees, or pi by 4. And so our point is at root 32, comma, pi by 4. Which is a very weird way of writing it, because normally you expect this to be x, and you expect this to be y. But now we have r and we have theta. But the whole point of a coordinate is it should tell you how to get to a point. If I said 4, 4, well, you would know to move 4 on the x and 4 on the y. But if I give you root 32 and pi by 4, you can still find where to place the point. You go out along the circles until you find the circle that has root 32 as the radius, which is about 5.5. And then you swing in until you get to pi by 4 as your angle. And then you can plot the point, no problem. So a point in these coordinates, which are called polar coordinates, is described using a radius, right? Think the length of that point, and an angle. And we write it as r comma theta. So let's practice. Let's plot the points 3 and 0 degrees, 4 and 45 degrees, 1 and pi, and so on. Let's plot these points on a polar grid. Well, let's start with the first one here. Do it in black. So 3 and 0 degrees. Well, we're going to assume here, just for argument's sake, that each one of these blue lines, I probably didn't show up on your photocopy, but you can see here on the video, each one of these blue rings is going to be a whole number. So this is going to be 1, 2, 3. So right here, we've got 3. Right, we could label these as 1, 2, 3, 4, 5, 6, and 7. So 3 is right there, and then we have to swing in, we swing in 0 degrees. So it's just right there on the axis. 3 and 0 degrees is right here. Let's try the next one. 4 and 45. Well, we go over to 4, and then we swing in to 45. So 4 and 45 would be right here. All right, let's do the next one. 1 and pi. Well, 1 is right here, and then we swing all the way around to pi, which is all the way on the other side. So that will be right here. 3 and 60. We'll go to 3 this time, same as before, and we swing on up to 60 right there. Let's try 2.5 and 3 pi over 4. Well, if we convert 3 pi over 4 to a degree, that's going to be 135. And 2.5 is between 2 and 3. So that little less dark line, the gray line between 2 and 3, and over at 135, that lines up right there. All right, let's try another one. 36 and root 36, and 3 pi over 2. Let's do that in gray. So we've got root 36. Well, let's simplify. We could simplify root 36 to just 6. And 3 pi over 2 is going to be, we know, at the bottom. So we're going to have 6 and 3 pi over 2. All right. So that should make sense. We have a coordinate, and we can clearly plot it on this grid. We just have to find the circle that we're going to follow, and then we follow the circle around the appropriate amount of angle. Let's see if we could go the other way. Could we convert a polar coordinate into rectangular coordinates? So if somebody told you 3 and 60 degrees, the one we had over here in green, could we convert this back into rectangular coordinates? Well, let's give it a whirl. So we had 3 and 60. That was our information. We would want to really know x and y. Well, I think we could use some trigonometry to find those. Solving for x. X is going to be adjacent, and 3 is hypotenuse, and y is opposite. So to find adjacent and hypotenuse, we could use cos. So cos 60 will be x over 3 multiplied by 3, so x is equal to cos 60 times 3. We could do y. Y is going to be sine. So sine of 60 equals opposite over hypotenuse. So y equals sine 60 times 3. Then we just need to do a little bit of unit circle knowledge. So cos of 60 is 1/2. So we get 1/2 times 3, or 3/2. And sine of 60 is root 3 over 2. And so we get 3 root 3 over 2. And so, yeah, we were able to convert our point 3, 60 into 3/2, 3 root 3 over 2. We could definitely convert our polar coordinate into a rectangular coordinate. Now, the formulas for this are worth memorizing. You can draw the triangle every time, but it's just faster to have these ready to go. So x goes with cos and y goes with sine, and you put an r in front. This should make sense from the unit circle. If you think about the values on the unit circle, the x value of the unit circle is the cos, the y value of the unit circle is the sine. It's just that we're not going to be on a unit circle, we're going to be on a circle of radius r, so you put an r in front. But it's basically your unit circle formulas. So let's go ahead and convert this polar coordinate into a rectangular coordinate. So x will equal 4 cos 3 pi over 4. Y will equal sine, forgot the 4 in front, 4 sine 3 pi over 4. So x will be 4 times negative root 2 over 2. And y will be 4 times root 2 over 2. So this, we can reduce the 4 and the 2, so this will be negative 2 root 2. And this will be 2 root 2. So So if you wanted, you could write it like this. You could have negative 2 root 2, comma 2 root 2. But you should probably mention that this is rectangular, so that you don't get confused, because if this is polar and this is rectangular, you want to make sure that you know which is which. Now let's go the other way. Let's convert rectangular coordinates into polar coordinates. So we're given the point negative 3 and 4. Let's see if we can figure that out in polar. Well, you can have formulas to go the other way, but it's just as easy probably to draw a diagram for this one. We know it's at negative 3 and 4. So 1, 2, 3, 1, 2, 3, 4. So there's our point. So to get to that point, we need, of course, a radius and an angle. Well, r, we could use a little bit of trig here. Negative 3 and 4. So r will be the square root of 3 squared plus 4 squared. So the square root of 9 plus 16. Square root of 25, which is 5. Now theta will be equal to, well, we have to do a reference angle first. And so our reference angle will be tan inverse of 4 over 3, which is not a nice number. You have to use your calculator. So this will be 53.130 degrees. Now, unfortunately, that's not a nice unit circle value, but you can use your calculator in some of these questions. And so if that's our reference angle, to find our actual angle, we're going to do 180 minus our reference angle. So 180 minus theta r will be theta. So theta will equal, this is degrees, 126.870 degrees. So there's our nice, beautiful polar coordinates, 5 and 127.870 degrees. This is polar. Now you might be wondering why to use polar coordinates, and there are actually many applications, especially in physics and in engineering, but one of the applications that's most useful to us is that we can write complex numbers really nicely in polar form. So, as an example, let's go ahead and convert the complex number 2 plus 2i into polar form. So notice we have 2 plus 2i, here's our complex number. Well, you can very clearly see that there's an angle, theta, and there's going to be a radius, r. There's a length of this line. So, let's go ahead and do our typical math. R will be equal to the square root of 2 squared plus 2 squared. So 4 plus 4, or root 8, which we could write as 4 times 2, so 2 root 2. And then we need to find theta. So theta, we'll do the reference angle, which is the same as the actual angle. So theta will be tan inverse, if you want, of 2 over 2, which if you use a calculator or you use your unit circle, this is actually a nice one. We know tan inverse of 1, it's just going to be 45 or pi by 4. It's always nicer to do things in radians, it just works a little bit nicer. So that means our number, let's call 2 plus 2i, let's call that the number z. So therefore, z is equal to 2 root 2. Well, how do we put the rest of it down, right? We could write 2 root 2 as the r, but then we have this theta business. So, I mean, I guess maybe we could just write it as a coordinate. We could write it as 2 root 2, comma, pi by 4. But then how do we know this is complex? Because this would just seem to indicate the regular number 2, comma 2, like a coordinate on a regular plane. How do we know this is the complex plane? It's a little bit ambiguous. And so to help differentiate from a real number in polar form, we're going to always write a complex number in polar form as follows. Z will equal r cos theta plus ir sine theta or r cos theta plus I sine theta. Now, what that means is we're writing it as if saying, okay, well, we have this complex number, which you can think of here as x plus yi, because it's gone over here an x amount, and it's gone up here a y amount in the I. So x, we found, is equal to, well, r cos theta using our formula, because x is going to be r cos theta from the last page, and y is going to be r sine theta. So once we find r and theta, we write our x value as our r cos theta, and we write our y value as our r sine theta, but we put that I in there to make sure we know it's a complex. So our example here, we would be z equals 2 root 2 for our r, and then cos pi by 4 plus I sine pi by 4. Now there's a big advantage to writing it this way. What's so helpful for this is it allows us to convert it back to a regular complex number just using our trig values. So we have z equals 2 root 2 cos pi by 4 plus I sine pi by 4. Which again, you might look at that and say, there is no way that this is the same as 2 plus 2i. Well, let's give it a whirl. Let's try to use our unit circle values. This will be root 2 over 2. This will be I root 2 over 2. So we'll get, well, when we multiply, we're going to get 2 root 2 times root 2. So that'll be, the root 2's can multiply to give us a 2. So this will be 2 times 2 over 2 plus I 2 times 2 over 2, which is 2 plus 2i. Same. Right? This is the same as this right here. And so we were able to get the same value by writing it and then expanding it, which of course means it's correct. But the nicer thing is that we're not going to get confused because is this complex? Well, there's no I there. It's hard to tell it's actually a complex number. But if we write it with the cos and the sine with the I next to it in that proper form, it'll look like a complex number. So let's do another example here. Let's convert the complex number 3 plus 4i into polar form, and we're going to give the answer to the nearest degree. So we can go ahead and draw the diagram just to refresh us of what formulas to use. So we have our little diagram here of 3 over and 4 up. So there's our point. And so we have 3 and 4 and r and theta. So r will be equal to the square root of 3 squared plus 4 squared. So 9 plus 16. So root 25, or just 5. Now theta, we'll use the reference angle, will be tan inverse of 4 over 3. We're going to need a calculator for that, so that'll be 53.130 degrees. So just let's go 53 degrees, round to the nearest degree, as said in the question. So then therefore, our complex number z is equal to 5 cos 53 degrees plus I sine 53 degrees. And if you wanted to expand it back from polar form into the 3 plus 4i form, you would just calculate cos of 53 and sine of 53. Now, if you do this on your calculator, you're not going to get exactly 3 plus 4i because we rounded here. But if you used this full answer, you would get back to the 3 plus 4i. So let's do one more here. Go ahead and pause the video and see if you can try this one on your own. Convert this complex number into polar form. Alright, assuming you gave this a try, we'll draw the diagram here. So it's 4, 1, 2, 3, 4, but then it's down 1. So it's over here. So we still got our radius, but our angle is going to be like that. So radius will equal the square root of 4 squared plus 1 squared. Just as a note here, this is technically down 1, so you could put negative 1 squared, but negative 1 squared is the same as 1 squared because the negative squares away. So either way, you get 1 from that. So 16 plus 1, so 17. And of course, 17 can't be square rooted. Now to find the angle, we're going to find the reference angle first. So we'll do tan inverse of 1 over 4, which will give us 14 degrees if we round to the nearest whole number. Now that means that this little angle in here is 14, so to find the full angle we have to do 360 minus. So theta is going to be 360 degrees minus the reference angle. So 360 degrees minus 14 degrees, and theta is going to be equal to 346. Well, that tells us then that we have z is equal to root 17 cos 346 degrees plus I sine 346 degrees. So go ahead and try these exercises. Make sure you're comfortable with plotting numbers in polar form, and then you can have some practice converting some complex numbers into polar form. As always, thanks for watching.